Hello students, welcome to session 3 on chapter 2 Relations and Functions. Before continuing our discussion, let us recall the concepts or points that we have studied in the last session. First we have discussed about Cartesian product of two non-empty sets. The Cartesian product of two non-empty sets, set A and set B, is equal to the set of all ordered pairs A, B, where A belongs to set A and B belongs to set B. Here, two ordered pairs are equal if and only if the corresponding first elements are equal and the second elements are also equal. If set A has m elements and set B has n elements, then A cross B will have m into n elements. Number of elements in the Cartesian product of two sets A and B is m into n. Then we have also discussed that our set of A cross B will have 2 to the power mn elements. Number of elements in the power set of A cross B is 2 to the power mn. Also, we have studied about relations. A relation from a non-empty set A to a non-empty set B is a subset of A cross B containing the elements A, B, where A belongs to the first set A and B belongs to set B and A is related to B under the given relation R. Then we say it is a relation. Therefore, relation is a subset of the Cartesian product of two non-empty sets A and B. Also, we studied that the set of all first elements of R, the set of all first elements of R is called domain of the relation. We have defined domain of the relation as the set of all first elements of the relation R, and the set of all second elements of the relation R is defined as range, and the set of all elements in the set B is known as codomain. A relation F from a non-empty set A to a non-empty set B is said to be a function if every element of set A has one and only one image in set B, and function, then it is called a function, and function F from set A to set B is denoted by this symbol. Then we discussed about domain and range of a function. The set of all elements in set A is called domain. The set of all elements in set B is called codomain. And set of all images of the elements in set A is called range. So range is equal to set of all F of A where A belongs to set A. Set of all images. Image of an element in set A is denoted by F of A. In general, we write image of an element in the domain as Y is equal to image of X under the relation F. Then it is called a function. In the last class, we have discussed one problem on functions. Now, let us go to another example in our textbook. Example number 11. Examine each of the following relations given below and state in each case giving reasons whether it is a function or not. First relation given is R is equal to 2, 1, then 3, 1. And 4, 2. This is a relation. We have to decide whether it is a function or not. Here, if we draw the arrow diagram for this relation, image of 2 is 1, image of 3 is also 1, and image of 4 is 2. Here, according to the definition of a function, every element in the domain should have an image, and image must be unique. Here every element in the domain has image 2, 3 and 4. All are having the image in the codomain. And no element has the two images. 2 has only one image, 3 has only one image, 4 has only one image. Therefore, it satisfies the conditions of a function. Therefore, R is a function. R is a function. Or in terms of ordered pairs, if you say no two ordered pairs have same first element here. All the ordered pairs have distinct first elements. Therefore, this relation is a function. If you go through the second example here, R is equal to 2, 2, 2, 4, 3, 3, 4, 4. If you draw the arrow diagram for this question number 2, 2 has the image 2, then 2 has the image 4 also, image of 2 is 4 and image of 3 is 3 and image of 4 is 4, image of 4 is 4. So here if we think of the definition of a function, here 2 has 2 images. According to the definition, no two ordered pairs can have the same first element. Here 2 has 2 images, therefore this is not a function. Second relation given in the question is not a function. In the third example, R is equal to 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7. Here if we observe 1, 2, 3, 4, 5 and 6 are the first elements of the ordered pairs and no element is repeated as the first element. Therefore, this relation is a function. So, in this question, first question is a function, second is not a function because 2 has 2 images and third one is a function. Next, the definition of real valued function and real function. A function which has either or one of its subsets as its range is called a real valued function. A function f from some set, okay, to set of real numbers or subset of real numbers. This codomain must be a set of real numbers or a subset of real numbers, maybe integers or few integers like set x containing the elements 1, 2, 3. This is also a subset of real numbers. If codomain is this type of set, then it is called real value function. Further, if its domain is also either set of real numbers or a subset of R, then it is called as real function. So, real value function states about the codomain, whereas the real function, okay, require the condition that the first set and second set both must be set of real numbers or subset of real numbers. Then it is called real function. So here we can observe that all real functions are real value functions, but all real value functions may not be real function. Next we are going to study some of the important functions, their graphs and also domains and ranges. First one is identity function. Let R be the set of real numbers. Define the real value function f from R to R by y is equal to f of x is equal to x for each x belongs to R is called identity function. A function f from R to R defined by f of x is equal to x for all x belongs to domain. Domain is set of real numbers here. This is the codomain. For each and every x in the domain, its image is same x, that x is maintained. Image of 1, if you give x is equal to 1, image of 1 is 1, image of 2 is 2, image of 3 is 3 and so on. We also define f of x as y, image of x as y. If we observe the graph of this function, Here if we give x is equal to 1, then value of y is also 1. If you give x is equal to 2, value of y is also 2. If you give x equal to 0, value of y is also 0. If you give x is equal to minus 1, value of y is also minus 1. Therefore, when we give x equal to 1, y is also 1. This is a point on the graph. When x equal to 2, y is also 2. When x is 3, y is also 3. When x is minus 1, y is also minus 1. When x is 0, y is also 0. If you collect all these points, we get the graph of identity function. So, which is a straight line passing through the origin. This is the graph of identity function. What is the domain of this function? The possible values of x is the domain. We can give any real number for x, therefore domain is equal to set of real numbers R. Domain is equal to set of all real numbers. Then value of y is also same, therefore range is also equal to set of real numbers. So that is about the identity function. We can see the graph of identity function here. For each value of x, the value of y is also same. Therefore 1, 1, 2, 2, 3, 3, 4, 4 and so on. In general we say x, x is a point on that identity function. And here the domain and range of f are. Next function is constant function. Define the function f from R to R by y is equal to f of x is equal to c, where c is any real number, is called constant function. F of x is equal to c. We can take any constant as the value of c as the constant here. For example, if we take f of x is equal to 3, then this is a constant function. If you take f of x equal to 4, f of x equal to 100, these are all constant functions. And if you plot the graph of this represents x-axis, y-axis, and this is the origin. And when we give x is equal to 1, value of y remains 3. Value of y is 3. When x is equal to 1, value of y is 3. When x is equal to 2, value of y is 3. When x is equal to 3, value of y is 3. When x is equal to 0, value of y is 3. When x is equal to minus 1, value of y is 3, and so on. Therefore, for each value of x, value of y is 3. Therefore, it gives the curve which is parallel to x-axis. In fact, it is a straight line parallel to x-axis. This is the graph. What is the domain? Domain of constant function is set of all real numbers. We can give any value to x from the set of real numbers. And here the range is equal to only one element, that is c. In this example, c is equal to 3. In general, range is equal to set of all images, and it has only one image, that is constant c. In this example, c is equal to 3. We can see that graph in the board here. Domain of this function is R, and its range is single element set containing the element c. Next function is polynomial function. A function f from R to R is said to be a polynomial function if for each x in R, y is equal to f of x is given by a0 plus a1x plus a2x square plus and so on up to an x power n, where n is a non-negative integer. Non-negative integer means integers greater than or equal to 0. And a0, a1, a2 up to an are real numbers. This is a polynomial function. If we give the values to a0, a1, a2 up to an, then you will get a particular polynomial function. We have the example here. Example number 13. Define the function f from R to R by y is equal to f of x is equal to x square, where x is any real number. The question is, what is the domain and the range of this function. Draw the graph of f. Here the given function is y is equal to f of x is equal to x square. This is a polynomial function. Here x is a real number. X can take any real number. Therefore, domain is equal to set of real numbers. Domain is set of real numbers. Now, if we plot the graph of this function, this represents x-axis and the vertical line represents y-axis. This is the origin here. 1, 2, 3, 4 are the points on x-axis. Now, if we plot the graph of this function by giving the values to x and y, as we have studied in our earlier classes, if we give x is equal to 0 here, f of 0, value of y is equal to f of 0 is equal to 0 square, 0 square is 0. If we give x is equal to 1, then y is equal to f of 1 is equal to 1 square is equal to 1. If we give x is equal to 2, then y is equal to f of 2 is equal to 2 square is 4. And if we give x is equal to say minus 1, then y is equal to f of minus 1 is equal to minus 1 square, which is also equal to 1. And if we give x is equal to minus 2, y is equal to f of minus 2 is equal to minus 2 square, which is equal to 4. So with these points on the graph, we can obtain the graph of the function. When we give x is equal to 0, value of y is also 0. When we give x equal to 1, value of y is also 1. When we give x equal to 2, value of y is 4. Now the function started increasing rapidly. When x is equal to minus 1, value of y is 1. When x is equal to minus 2, value of y is 4. Therefore, we can observe the graph of the function like this. And this is called parabola that we are going to study in our first PUC syllabus. Now we shall see the graph of this function in the PPT here. F of x equal to x square, this is the graph of the function, and domain is equal to set of all real numbers here, and domain is any real number we can give. So and set of all images is equal to range. Range can be written as set of all x squared where x belongs to the domain. Set of all x squared where x belongs to the domain is the range of this function. We have one more example here, example 14. Draw the graph of the function f from R to R defined by f of x equal to x cube, where x is any real number. F of x is equal to x cube, where x belongs to R. If we plot the graph of this, first let us give the values to x and calculate the value of y. When x is equal to say 0, y is equal to f of 0 is equal to 0 cube is 0. When x is equal to 1, f of 1 is equal to 1 cube is 1. And when x is equal to 2 cube is 8. And when x is equal to 3, we can observe that f of 3 is 3 cube is 27, and so on, the function is increasing. Next, when we give negative values to x, when we give minus 1, f of minus 1 is minus 1 whole cube is minus 1. And when we give x equal to minus 2 whole cube is minus 8. And when we give x is equal to minus 3, f of minus 3 equal to minus 3 whole cube, that is minus 27. These are the values, the points on the graph. So by knowing this information, if we plot the graph of this function, here we have integral points on x-axis and the integral points on y-axis. When we give x is equal to 0, y is also 0. Therefore, 0, 0 is a point on the graph. 0, 0 is a point. Next, when we give x equal to 1, y is equal to 1. So 1, 1 is a point on the graph. Next, Next, when we give x equal to 2, y is equal to 8. When x equal to 2, y is equal to 8 somewhere. It's rapidly increasing. When x equal to minus 1, value of y is also minus 1. When x equal to minus 2, value of y is minus 8 somewhere here. So if we join all these points and draw the graph of this function, we get a curve like this. This is the graph of y is equal to x cube. What is the domain of this function? Domain is equal to, we can give any value to x. Therefore, set of real numbers is the domain. In fact, this function f is defined from R to R. Whenever we say it is a function, all the elements in this first sector must have the image. Therefore, all the elements in the first sector of a function is domain. It comes under domain. Therefore, domain is equal to the set of all elements in this first set. Therefore, first set itself is the domain of a function. And range is equal to set of all images is equal to set of all x cube, where x belongs to domain. For all the values of x, we have its cube. That is, the set of all those numbers is the range. We can see the graph of that function, f of x equal to x cube. Next is a rational function. Rational functions are functions of the type f of x divided by g of x. We define rational numbers. Similarly, we define rational functions as functions of the type f of x divided by g of x, where f of x and g of x are polynomial functions of x. Already we have discussed about polynomial functions like f of x is equal to a0 plus a1 into x plus a2 into x squared and so on up to an into x power n, where n is a non-negative integer. So that type of functions are f and g. Polynomial functions of x defined in a domain where g of x should not be equal to 0 for any x in the domain, because g of x is in the denominator. If the denominator is 0, value is not defined. Therefore, functions of this type f of x by g of x are called polynomial functions. For example, f of x is equal to say x plus 1 divided by x squared plus 2 is a polynomial function. Here we have an example. Define the real value function f from R minus set containing element 0 to R defined by f of x equal to 1 by x, where x belongs to R minus 0. Because here we cannot give the value of x equal to 0, because f of 0 is 1 by 0, which is not a real number, it is not defined. We say its value tends to infinity. Now the question is here, what is the domain and range of this function? What is the domain and range of this function? Now we can see this function f from R minus 0 mapping to R defined by f of x is equal to 1 by x. Now if we analyze the graph of this function, we cannot give x is equal to 0 because 0 is not there in the domain. Then we give x is equal to say 1 by 2 half, then this 1 by 1 by 2 is equal to 2. If you give x is equal to 1, then its value is 1 by 1 is 1. If you give x is equal to 2, its value is 1 by 2. If you give x is equal to 3, f of 3 is 1 by 3 and so on. And if you give the negative values to x, say minus 1 by 4, then its value is a minus 1 by 4, that is minus 4. And if you give x equal to minus 1, its value is 1 by minus 1, which is equal to minus 1. If you give x equal to minus 2, its value is 1 by minus 2, minus half and so on. By knowing these many points on the graph, we can think of plotting the graph of the function here. This is the origin. When we give x equal to half somewhere here, value of y is 2. For x equal to half, value of y is 2. Somewhere here. And when we give x is equal to 1, value of y is 1. When x is 1, value of y is 1. When x is half, value of y is 2. When x is 1, value of y is 1. When x equal to 2, value of y is half. So we can observe that the graph is decreasing here. So in that part, the function goes like this for all positive values of x. We cannot give x equal to 0. When we give x equal to negative values like minus 1 by 4 somewhere here, minus 1 by 4, then image or value of y is minus 4 somewhere here. And when x equal to minus 1, value of y is also minus 1. And when x is equal to minus 2, value of y is minus half. So this is the nature of this graph. So this is the graph of the function f of x equal to 1 by x. If you think of the domain of this function, it is already given in the function. Domain is equal to set of all possible values of x, that is equal to set of real numbers except one element, that is 0. And what is the range? Range is equal to set of all real numbers. Range is equal to set of all images is equal to set of all real numbers, but it never takes 0. This value of 1 by x never becomes 0 for any value of x belongs to the set r minus 0. Therefore, range is r minus single element set containing 0. You can see the graph of this function here. The domain of this function is all real numbers except 0, and range is also all real numbers except 0. Next function we are going to study is modulus function. The function f from r to r defined by f of x equal to mod x for each x belongs to set of real numbers is called modulus function, or we define it as f of x equal to x if x greater than or equal to 0 minus x if x is less than 0. So modulus function means is a function which gives positive value or 0 value for all x belongs to r. F of x equal to mod x is equal to if x is greater than 0, it is 0 if x is equal to 0, and minus x if x is less than 0. Or combining these two conditions, x greater than or equal to 0, value of mod x is x, because when x equal to 0, modulus of 0 is 0 only. So mod of a function always gives non-negative value. That is, if mod of minus 2 is to be calculated, value of minus 2, modulus of minus 2 is equal to 2. Whereas modulus of 2 is also equal to 2, because it always gives non-negative value. Modulus of minus 3 is equal to 3, modulus of minus 1.5 is equal to 1.5. This is the function which gives always non-negative value. Modulus of 0, if you calculate, it is 0 only, no change. So mod value or mod function can take all non-negative real numbers. If we think of plotting the graph of this, function, this represents x-axis, this represents y-axis, and here we have positive real numbers, and here we have negative numbers on x-axis. Here we have 1, 2, 3 integer values on y-axis. When we give x is equal to 0 here, f of 0 is mod 0 is equal to 0. So this is 1 point. Then when we give x is equal to 1, mod 1 is 1. So this is another point. When we give x equal to 2, that is also value greater than 0. Then modulus of 2 is 2 only. And when we give x is equal to 3, modulus of 3 is 3, and so on. So for all x equal to 0, it is 0, and for all x greater than 0, this is the graph of that function. And when we give x is equal to negative values like minus 1, then modulus of minus 1 is plus 1. Let us give x equal to minus 2. Modulus of minus 2 means x is less than 0. X is less than 0. Minus of minus 2 is 2. That is the definition. When x is equal to say minus 3, x is less than 0, that is minus 3. Then modulus of minus 3 is minus of x, that is minus of minus 3, that is 3, and so on. So if we join all these points, we get the graph of f of x equal to mod x. This is the function, and this is a very important function that plays very important role even in our second PUC also. So this is an important function to be understood. Modulus of x always gives non-negative real number. Here minus x doesn't mean that it is negative. This is also a positive quantity only. This is positive quantity because x is already negative. Negative into negative gives you positive quantity. You can see the graph of modulus function here. It always takes positive values or 0. The domain of modulus function is all real numbers. We can give any value to x from x-axis. Means it takes all the real numbers. And range is equal to set of all non-negative real numbers. It never takes negative values. Then next function is signum function. This is another important function that we have to understand. The function f from R to R defined by f of x equal to 1 if x is greater than 0. For all x greater than 0, f of x takes the value only 1. Like for all x greater than 0, it is a constant function. And if x equal to 0, f of x equal to 0. And if x is less than 0, f of x equal to minus 1. Means for all x less than 0, f of x is again like a constant function. It takes the value only minus 1. This is called signum function. If we see the graph of this function, here f of x is equal to 1 if x is greater than 0. It is equal to 0 if x equal to 0. And it is equal to minus 1 if x is less than 0. Now if we plot the graph of this function, if we give x is equal to 0 here, when x is equal to 0, value of the function is f of 0 is equal to 0. So this is the point on the graph. Next, when we give x positive, x greater than 0, say x equal to 1. When x is equal to 1, f of 1 is equal to 1. F of 1 is equal to 1. This is the point on the graph. When we give x is equal to 2, f of 2 is equal to 1. F of 2 is also equal to 1. When we give x equal to 3, f of 3 is also equal to 1. When we give x equal to 4, f of 4 is also equal to 1. So for all x greater than 0, this is a constant function like this. This is a constant function like this. But when x equal to 0, its value is 0, not 1. Therefore here we have to write a small circle indicating that when x equal to 0, this is not the value. For all x greater than 0, this is the value. 1 is the answer, 1 is the image. Therefore, we have to write a small circle indicating that, excluding that point. Okay? Value of the function f of x is 1 for all x greater than 0. When x equal to 0, this is not the value. When x equal to 0, this is the value. And for all x less than 0, let us give x equal to minus 1. F of minus 1 equal to minus 1. When we give x equal to minus 2, f of minus 2 is also minus 1. When we give x equal to minus 3, f of minus 3 is also equal to minus 1. So for all x less than 0, this is the graph of the function. But when x equal to 0, this is not the value. So we have to write a small circle here indicating that when x equal to 0, this is not the image of f of 0. This is not the image of f of 0. F of 0 equal to 0, and for all x less than 0, its value is minus 1. For all x greater than 0, however close it may be to the value 0, its image is 1. But when x equal to 0, its image is 0. So this is about the signum function. And if you observe this, we can give any value to x. Therefore, its domain is equal to set of all real numbers. Domain is equal to set of all real numbers. And what is the range? Range has only 3 elements. It can take minus 1, 0 or 1. It has only 3 images. It takes either 0 or 1 for all x greater than 0, or it takes minus 1 for all x less than 0. Therefore, this is the range of signum function. Let us see the graph of this here. F of x equal to Signum function can also be represented as f of x is equal to mod x by x, because we have already studied about mod x. This is the definition for x not equal to 0. That is very important. This is not true for each and every x. And we can say it is equal to 0 if x equal to 0. So signum function is mod x by x if x not equal to 0. Means for x greater than 0, mod x is x by x equal to 1. And for x less than 0, mod x is minus x divided by x equal to minus 1. And when x equal to 0, it is equal to 0. So signum function can also be defined as f of x equal to mod x by x when x not equal to 0, and it is equal to 0 when x is equal to 0. Next function we are going to study is the greatest integer function. The function f from R to R defined by f of x equal to square bracket x, which indicates greatest integer function, where this square bracket x means the value of the greatest integer less than or equal to x. Such a function is called greatest integer function. Square bracket x means it takes the greatest integer less than or equal to the given number. For example, this is the number line. The center 0, 1, 2, 3, minus 1, minus 2, minus 3. When we take the greatest integer part of 0, its answer is 0. Greatest integer part of say 1.5 is the greatest integer but less than or equal to 1.5. It should be an integer, and among all the integers it must be greatest, and it should be less than 1.5. So 1.5 is between 1 and 2. Greatest integer less than or equal to 1.5 is 1. Next, greatest integer part of say 2.9. 2.9 comes somewhere between 2 and 3. Greatest integer which is less than or equal to 2.9, that is equal to 2. 1 is also the integer less than 2.9. 0 is also the integer less than 2.9. Minus 1, minus 2, minus 3 are all the integers less than 2.9. But among all these integers less than 2.9, greatest is 2. Suppose the given number itself is an integer, then it is equal to integer. Therefore, this is the greatest integer. This is the greatest integer less than or equal to x. Equal to x when x is an integer. Otherwise, it is less than x. So, it is the greatest integer less than or equal to x, called greatest integer function. Now, let us see some more examples. Like greatest integer part of minus 0.5. What is this? Greatest integer part of minus 1.6. What is the greatest integer part of minus 2.5? If you observe that on the number line, here we have 0, minus 1, minus 2 and so on. Minus 3. Greatest integer part of minus 0.5. Minus 0.5 comes between 0 and minus 1. And greatest integer less than or equal to this is minus 1. It is minus 1. Greatest integer less than or equal to minus 0.5 is minus 1. Greatest integer less than or equal to minus 1.6. Minus 1.6 comes in between minus 1 and minus 2. And greatest integer part of that, the greatest integer less than or equal to minus 1.6 is minus 2. You can clearly observe that on the number line. Minus 2.5 comes between minus 2 and minus 3. Then the greatest integer less than or equal to minus 2.5 is minus 3. Among all the integers less than or equal to the given number, which is the greatest? That is greatest integer function. Okay, this function is called greatest integer function. Let us see the graph of this function now. Let us draw the x-axis and y-axis which represents a plane now. Now, when we give x is equal to 0, greatest integer part of 0 is 0. When we give x equal to 0.5, greatest integer part of that is 0. When we give x equal to 1, its value is 1. 1. So, when we give x equal to 0, it is 0. When we give 0.9, greatest integer part of 0.9 is 0. So, between these two, this is the function. But when x equal to 1, it is not 0. when x equal to 1, integer part is 1. Then between 1 and 2, here, between 1 and 2, if you give 1.5, greatest integer part of that is 1. Then we give 1.9, greatest integer part is 1. So this is the graph of the function. This is the graph here between 0 and 1. Between 1 and 2, the graph value is 1, but when x equal to 2, it is not the answer. When x equal to 2, greatest integer part is 2 only. When x equal to 2, greatest integer part of 2 is 2. And between 2 and 3, it takes the value 2. When x equal to 3, this is not the value, it is equal to 3. When x equal to 3, function value is 3. And so on. This is also known as step function. Here, when x equal to minus 1 or minus 2, minus 3, we can observe here between minus 1 and 0, greatest integer function is minus 1. So here it is minus 1. But when x equal to 0, it is not minus 1. So we have to circle here, means that it is not the answer, it is not the image. When x lies between minus 1 and minus 2, it takes the value minus 2. It takes the value minus 2. But when x equal to minus 1, it is not the answer. So this is the graph that we are getting for the greatest integer function. What is the domain of this function now? Here domain is equal to set of all real numbers. We don't have restriction from giving the values to x. We can give any value to x from the set of all real numbers. Therefore domain is equal to. And what is the range? Range is, since this function is taking only integer values, range is equal to set of all integers z. So let us see the graph of this function now. This is the graph of the function. Between 0 and 1, it takes the value 0. But when x equal to 1, it takes the value 1. When between 1 and 2, function takes the value, between 1 and 2, function takes the value 1. But when x is equal to 2, it is not 1, it is equal to 2. Between 2 and 3, function takes the value 2. But when x equal to 3, it is not 2, it takes the value 3. Between here 3 and 4, function takes the value 3, but when x equal to 4, it is not 3, it takes the value 4, and so on. Here also, between minus 1 and 0, it takes the value minus 1, but it is not so when x is equal to 0. Between minus 2 and minus 1, it takes the value minus 2, greatest integer less than or equal to that. But when x equal to minus 1, minus 2 is not the answer. It is actually minus 1, and so on. This is called greatest integer function. And its domain is set of all real numbers, and range is also set of all. Domain is set of real numbers, and range is equal to set of integers. With this, let us conclude this session, and we will continue in the next session. Thank you.